Okay. Hi, everybody. One student, Ayong, told me that I make mistake in my video. I forgot which I believe that's the video from lesson 8. Let me see. What question was that? Do you remember what question is this, by the way, the one that I went over in my video?
Number 8.
Number 8 from 2.7, huh?
Yes.
Section 2.7, number 8. It's number 8. When I went over that in my lecture video, I unintentionally changed this here becomes 4. I wrote 4 instead of the correct 7. And I think then the result gets also wrong. Okay, but here's the thing then, to clarify that further, that how do we get the domain, Thomas, the domain of this? Well, first, the domain of the quotient of two function has to be, give me a second. Yeah, the domain of the quotient of two function has to be the domain of the original f. This is the function f. Okay, the domain is all real number except 2. Now, and then gx, the domain is all real number except -4. Okay, but we have additional rule that the gx cannot be 0. Gx cannot be 0. Okay, from there we see that's how we put them together. And this is a further explanation how I get those. Yeah, this is video from lesson 8. This is video from lesson 8. Okay, now, like what I said, we are a little bit behind schedule. Let me finish up this 2.5 and 2.6, and then I go on with 2.7. Then I go on with 2.7. 2.5 first. Piecewise defined function. That's a function that is defined piece by piece. Now, I hope you already watched my lesson 7. We are, like what I said, we are a little bit behind schedule, right? Okay, so you can see this from in lesson 7, while we are actually already in meeting number 8. We're supposed to be working on lesson 8. But this is from lesson number 7. Piecewise defined function. I went over it there, but let's do example here. So how do we do this problem? Let me grab my graphing paper so that it looks better later on. Where's my graphing paper? Okay, this is my graphing paper. Let me move it up a bit. Okay, now, then we have 2 pieces here. This is the first piece. And it is for x at most -1. So this is x at most -1. Now, to the left of that, we will apply this function. Absolute of x plus 3. Now, absolute of x plus 3 on just that region for x at most -1. So how do I do that? Absolute of x plus 3 is absolute of x. You move 3 units to the left, right? Okay, so the vertex originally 0, 0, move 3 units to the left, the vertex becomes -3, 0. Then from there, you build the graph of absolute of x plus 3. Okay, now, so from here, I'm supposed to go this way, right? Supposed to continue, right? Supposed to. But according to that rule, it says that this function only works in x less than equals to -1. That's why then, no, I need to erase this part only up to x equals to -1. Now the left-hand side is still this one here. Okay. So the shape is absolute value shape, but the graph is truncated. Now then, when x is greater than -1, so from -1 but not including -1, going to the right, we will use this function. Now, what is that function? That function is -x plus 2. The y-intercept is 0, 2, but the slope is -1. So the slope is -1. So I basically connect all these points here. But this one, it will go up here, like that. Okay, so the one in yellow is this absolute of x plus 3. And then the one in blue, the blue highlight is -x plus 2, like that. Yeah, that's basically it. When you graph this piecewise defined function, you basically graph pieces of functions correspond to the given domain. Okay, so that's what it looks like. Okay, of course, you can make it nicer if you use ruler, right? Now, but before we go on, let's talk a little bit about the limit thingy. As x going to -1 from the right-hand side, what will fx approaching to in this function? When you approach x equals to -1 from the right-hand side, what is the value of y you are getting close to?
+2.
Huh? Is it +2?
+3.
+3. Yes, that's right. +3. When you approach from the right-hand side, okay? When you approach from the right-hand side, that's +3. If you approach from the left-hand side as x approaching -1 from the left-hand side, then what will the value of the function approaching to? Now, that's the one approaching to. Okay, now, so you see in calculus later on, we will write those notation as limit x approaching -1 from the right-hand side of that function is 3, while limit x approaching -1 from the left-hand side of the function is +2. Okay, that's the notation. That's example 1. Let's do one more example. You do it though. I would like you to do this. By the way, I already went over in full, I think 4 previous tests in my Monday, Wednesday recording. Okay, so please take a look and study from that. Your test is 2 weeks from now. Is it right? Yeah, on the 25th. So let fx equals to, let me make it 3 pieces right now. Let me make it 3 pieces right now. Let fx equal to, what is good? Negative of x plus 4 squared plus, no, not x plus 4. Maybe x plus 3 instead. Plus 4. And that's for x less than negative 2. And then how about absolute of x minus 1 minus 3 for x between negative 2 and what is good? Negative 2 and 1. And how about negative 2x plus 7 for x greater than 1. Okay, let me ask you to try that. How many minutes? 5 minutes maybe? Will that be good? So this one here, not including negative 2. And then this one here, from negative 2 up to 1, including 1. And then the last one, greater than 1 up to infinity. Okay, so basically instead of asking you 3 questions to graph 3 functions, I just do it this way. Okay, you do it 4 or 5 more minutes. Okay, I start graphing it already. Yeah, the last one, the one in green, it seems to be easier to graph, so I graph that one first. How about absolute of x minus 1 minus 3? So the vertex is at 1, 3. Opens up, so it's supposed to look like this, but it starts from 1, so I don't need to do one on the right hand side, just go to the left. It goes this way. It's a line. Forgive me. So it looks like that. And then the last one, the one in yellow, is from the vertex is negative 3, 4, but it's upside down. Hold on, that's including the endpoints though. Give me a second. This one includes the endpoint. That includes the endpoint, like this. But then for the quadratic, that will be up to -2, not including -2. So it looks like this here, and then this point, and then this point, and then this point. So it looks like this is piece of that quadratic. Okay, that's what it looks like. Approximately, that's what it looks like. Yeah. Oh. I try to clean it up. I end up erasing it. Yeah, that's what it looks like. Okay. I hope this is enough. Now let's move on to quadratic function. I believe I already did a very extensive lecture on my video. So again, we will do just problems here. But I need to emphasize the following. Emphasis, let the quadratic function fx equals to ax squared plus bx plus c. Then the first node, the graph opens up if the leading coefficient is positive, opens down if the leading coefficient is negative. That's one. Second, okay, the axis of symmetry can be obtained by x equals to the midpoint of the x-intercepts. Or we can also use x equals to -b over 2a. Now keep in mind that it has to be written as an equation of vertical line. In other words, it has to be x equals constant. Okay. Now, second, the vertex, we denote that by h comma k, just to help, has x component, the h equals to the constant from axis of symmetry. Okay, so the h here is equal to the constant you have from axis of symmetry. Now, while the k, the y component, may be obtained with two different ways. Two different ways. First one, you plug that h into the function to get the k. Or you can also use k equals to negative discriminant over 4a. Okay, now last part, which is the consequence of this vertex, is that if you have leading coefficient positive, which means it opens up, right? Now, then the vertex gives us the minimum value. Okay, while if the leading coefficient is negative, which means the parabola opens down, then the vertex is the maximum. Okay, important notes. So let's start with, for example, let fx equals to x squared minus what is good? X squared minus 2x minus 8. And we would like to answer these questions. First one, what's the y-intercept? I think that one is easy. Okay, and then second one, what's the x-intercept? And then the third one, what's the axis of symmetry? And then the fourth one, what is the vertex? And then after that, we will get the range. And how about the standard form? And then we will graph that. Okay, but let's get this first. Let's get this first. The y-intercept clearly is 0, negative 8. That's Mickey Mouse, right? You plug in x equals to 0, right? F0 equals to 0 minus 8, right? How about the x-intercept? You set the function equals to 0 and then solve it. Now you may need to solve it by, beside by factoring, realize that you can solve it also by completing the square or using quadratic formula if you cannot factor it. But if you are able to, if it is factorable, you need to factor it. Okay, otherwise I will penalize 1 point. So the x-intercepts are 4, 0, negative 2, 0. Now how about axis of symmetry? Axis of symmetry is x equals to, I have very nice x-intercepts here. Let me just use them. The midpoint of the x-intercepts. That's 2 over 2, that's equals to 1. So the axis of symmetry is x equals to 1. And then the vertex will be, 1 comma something, right? Now what is that thing? Then I plug that 1 into the function x squared minus 2x minus 8. That will be negative 9. Right, so the vertex is 1 comma negative 9. And the range will be, it opens up, right? So it will start from negative 9 to infinity. The standard form will be fx equals to a, which is 1, x minus 1 squared minus 9. How do you get that, Thomas? From the vertex. This is my h. This is my k. Okay, now let's take a look at the graph. Oh, it seems like my graph is not good. Let me do this then. I wonder if I can do it this way. Let me use this. Too small. How about this one? Too big. Let me use this for now. Screenshot this. And then go back to lines. So this is the x-axis. And this is the y-axis. Okay, it's kind of hard to see, huh? Yeah, it's kind of hard to see. That's why, I prefer to do copy paste. So the vertex is 1, -9. 1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the vertex. Okay, and then from there, I will build the left, right 1 units up 1, left, right 2 units up 4, left, right 3 units up 9. Okay, left, right 4 units up 16. So the graph of the function is now, let me bubble it bigger. So the graph of the function is now look like this. Now the question then is, what happened, Thomas, if I don't have printer during my in the test? Now I strongly suggest you to print out the graphing paper, or get a graphing paper. Okay, prepare graphing paper. Okay, prepare graphing paper, such that when you graph it, you just need to bubble it for important coordinates. Okay, for the important coordinates, you just need to bubble it. Now, otherwise, imagine if you don't have graphing paper. Imagine if you don't have graphing paper, then you need to do it this way. Okay, imagine if you don't have graphing paper, right? Then you need to name the position. Like this one, you need to put this is 4, 0. This is -2, 0. This is 1, -9. This is 2, -8. This is 0, -8. You need to label those important coordinates if you don't have graphic paper. Why? Because it doesn't really tell me what's the coordinate here until you label it, right? But then if you have graphing paper, then you don't need to do such thing anymore because your graphing paper already tells me the position, right? So let's do it again. Suppose I don't use graphing paper, right? Suppose I don't use graphing paper. So this is my x-axis, and then this is my y-axis. And then the coordinate is 4, 0. You just put 4, 0 and -2, 0. Okay, -2, -1, 9, and then you graph like that, right? But you see that this graph does not tell me anything though. This graph doesn't tell me anything. You say, oh, this is my graph, Thomas. Okay, then what are these coordinates? You don't even scale it. You don't even try to scale it. You just put it there. That's what it looks like. And Thomas, you figure out what are those. Well, my question to you is, you need to, you are the one supposed to give me the detail, not me giving you the detail. Okay? Yeah, you're the one supposed to give me the detail. So if you don't have graphing paper, then you need to label it. Oh, Thomas, this is my 1, -9. This is my 2, -8. This is my 3, 3, oh, that's 1. No, that's 3, something here. This is 3 comma -5, and then this is my 4 comma 0, and this is my, see, that's what you need to do if you don't have graphing paper. Okay. If no graphing paper. Is it okay? Give me a second. How about you try to do this? You do it. For example, this one is on the hard side. Let fx equals to -1/2 x squared minus x plus 10. Hold on. Plus, what is good? Plus 6, so that it fits my graph. Hope so. Okay, try this. Try this one. Find the y-intercept that should be on the easy side. And B, the x-intercept. And then the C, axis of symmetry. And then the D, the vertex. And then E, the range. F, the standard form. And then finally the graph. I think for the x-intercept here, I don't think it's factorable. Yeah, I don't think it's factorable. I mean, I don't think you can solve it by factoring. It's not factorable. So either you use formula or you use completing the square. Let me change one thing. This becomes out of range. Change this 6 becomes 5. Change that 6 becomes 5. Let me give you 5 more minutes. Or should I start working on this? Let me just start working on this instead of me doing nothing. This is 0.5. Yeah, you will have some resistance for doing the x-intercept. So 0 equals to -1/2 x squared minus x plus 5. Multiply both sides by 2, -2. That will give me 0 equals to x squared plus 2x minus 10. And then Let me do completing the square. So I add 1 to both sides. So I'll get 11 equals to x plus 1 squared. So plus minus square root of 11 equals to x plus 1. So x is -1 plus minus square root of 11. My x-intercepts are -1 plus square root of 11 comma 0 and -1 minus square root of 11 comma 0. How about my axis of symmetry? That will be x equals to -1, but let me work it out properly. That's negative b over 2a. So x equals to 1 over -1. So the axis of symmetry x equals to -1. Now how about the vertex? F -1 equals to, that's -1/2 times -1 squared minus -1 plus 5. That's -1/2 plus 6. That's 5.5. So the vertex is -1, 5.5. Or 11 over 2, right? So the standard form will be fx equals to -1/2 x minus h squared plus k. Okay, now let's see. The vertex is now -1, 5.5 is here. And because of that -1/2, when I move left, right 1 unit, left, right 1 unit, supposed to go up 1, right? But because of the -1/2, I go down half. When I go left, right 2 units, I supposed to go up 4, but because of that -1/2, I go down 2. So from here, 2 units to the right, I go down 2. When I go left, right 3 units, I supposed to go up 9, but because of that -1/2, I go down 9/2, which is go down 4.5. Right, so when I move 3 units to the right, I go down 4.5. Let's do more. If I move 4 units to the left, right, I supposed to go up 16, but because of that -1/2, I go down 8. So go 4 to the right, go down 8, 5.5, and then 2.5. Okay. Just for completion, what if I move left, right 5 units? So it's supposed to go up 25, but because of that -1/2, I go down 12.5. Okay. So go down, it will be here. So the graph will then, I get as many points as possible to help me graphing it accurately. By doing so, you are accurate at least at those important coordinates. Okay, the one I bubble. Okay. Now you can see that the x-intercepts are here and here. Okay, the x-intercepts, this one here is -1 plus square root of 11, comma 0. This one here, that's -1 minus square root of 11, comma 0. And the vertex here is -1, comma 11 over 2. Okay, that's the this from this 2.6. Okay, now before I leave this section, I would like to go over one question that I did in the past on one of our old quiz or one of our old tests. I have question coming in. Why is the vertex 11 over 2? The vertex is -1, comma 5.5. But 5.5 can be written as 11 point. That's 11 over 2, right? When you solve this, right? That's 11 over 2. That's how I get that 5.5. Okay. Now, from here, then I will answer one question like this. I went over this question yesterday, this type of question yesterday, but let me create another problem. So suppose, for example, the perimeter of a rectangle is, let's say, 20. Okay, we will do the following steps. To find the maximum area possible for that rectangle. Okay, so our first step is let x be the length. Okay, express the width in terms of x. I don't get it, Thomas. Okay, slow down, slow down. Okay, we have a rectangle. We have a rectangle. Listen to this. Once you've read a question or you hear a question, your next reaction is supposed to be, give me some time. Let me think about it. That's the correct reaction. Saying, I don't get it. It's like you push back and don't want to think. You want other people to think for you. Now, the thing is this though. First, in your test, you need to think for yourself. Okay, nobody will explain the question for you. Okay, that's one. Second, even in real life, even in real life. I mean, we have problems in real life, right? Now, what do you do if you don't understand what situation you are in? Do you give up? Then you will be part of the problems, right? A lot of problems we have in our daily life are because of those people don't solve problems, but they create problems. Okay. Now, the reason you are in this class and the reason you come back to school so that you can be a problem solver. Okay. If you can't even solve your own problem, then you cannot solve other people's problem. Okay. Like, I mean, regardless you believe me or not, but eventually, trust me, that's what you will face. Okay. You will only be a problem or problem solver. Okay. What I want you to be, and that's what I try to train you with, is to be a problem solver. But to be a problem solver, you need to think. Okay. Just to say, I don't get it. It's really you push back and you don't want to solve that problem. Then, even though it's not your problem, you can never be somebody else's problem solver because you always push back. Okay. No. Okay. Tell yourself, you know what? Give me some time. Let me think about it. Okay. Easy problem must be so easy that people don't even ask you. Hard problem must be hard enough such that it requires some skill to solve it. Now, some people don't have that skill yet. That's why they come to you, right? Okay. Now, let's say this is our length. Let's say we have a rectangle. This is our length, and this is our width. Okay. Now we know that the perimeter of a rectangle is twice the length plus twice the width. Is it right? Now, of course, if you don't know this fact, drop the class. Why? You're supposed to know this even from your Algebra 1, but it was emphasized again in your geometry. Right? Okay? No. Don't drop the class. Don't drop the class. You may just forget it. But I don't think I expect too much when I say that you're supposed to memorize the formula for perimeter of a rectangle. Okay? Now, perimeter is 20. That's what we know. The L says, call that L as an X. Now then express the width in terms of X. So you need to solve for this W. Okay, you see, what I have done so far here is really to translate the word problems into my picture, and then from that picture, I translate that to algebra. Okay, now don't just say, oh, I read the problem, I don't get it, Thomas. Well, trust me, if you don't read the problem, you don't get it, you just either you don't want to think or you cannot even read. I mean, whatever you read, you don't get it anyway. It could be the case, right? Okay, no, but of course, what the reason we are here is so that we can improve. Now then, slow down. Give me some time to think, Thomas. Let me draw the rectangle first. Okay. If you read it and you know what to do right away, like you know the equation right away, that W equals to what right away, either you're so smart or you get it wrong. You just don't get it at all. No, even Thomas need to write something down. Okay. Okay, 20 minus 2x equals to 2w. Now I divide both sides by 2 to solve for that w. Oh, I can simplify that. That's 10 minus x. Okay, now then, the second step, write the area function, the area as a function of x. Write the area as a function of x. So we know area of a rectangle is length times width. Okay, now replace the L and W in terms of x. Then all of a sudden on the left-hand side, it becomes a function of x. Is it okay? So ax is equal to negative x squared plus 10x. Why I feel like it's so small there? Should I use this one instead? Yeah. Now, if you think about it, you see, oh, that area is now a quadratic function, right? Now, and the leading coefficient is negative. This is quadratic. And leading coefficient is negative. So it has maximum value. Okay, now then step 3, find the maximum value, the y, okay, of that quadratic function. If you want to find the x, that's the axis of symmetry, okay? At what x will the area be maximum? Okay, but the question here is, what is the maximum area? The maximum area is basically the y maximum. Okay, the y maximum is negative d over 4a. Thomas, where do you get that? Let's look back very far to very beginning. See, if you want to know the y component of your vertex, one way to do it is by having negative d over 4a. You can also first find the x component of the vertex, which is the axis of symmetry, and then plug that into the function. You can do that also. Okay, you can do that also. Now let me do the second method first, the maximum area, the y maximum, or the maximum area is equals to negative d over 4a. That's negative of, what is my d? b squared minus 4ac. The constant is 0, right? Over 4a. That's equals to negative 100 over negative 4. That's 25. Okay. In other words, given the perimeter of a rectangle be 20, let's say 20 centimeters, then the area is at most 25. Cannot be more than that. So if somebody tried to date you, you know what? I can create a rectangle whose perimeter is 20, but the area is 30. You just say to that person, BS, you are lying through your teeth. I know my math and you don't. Right? Okay. You catch a cheater on the first date. No, it won't be. It won't be. Okay. Now that's the first method though. That's method number 1. The second method, if you want to play the movie a bit slower, then you can say, oh, you know what? My axis, my area function is x times 10 minus x, right? So the x-intercepts will be, when I set the area to be 0, so I get x equals to 0, x equals to 10. Can I change it to the standard form and find the area? You can, but when you change it to standard form, you need to find the vertex. And when you find the vertex, you need to find the y component of the vertex, which is your answer already. Right? So the question is, can you change it to standard form? Yes. Can you get the area from standard form? Yes. Okay. But in between, when you try to get that standard form, So standard form. And then from there, you try to find the maximum, right? But before you get the standard form, you need to get the vertex. Now, before you get the vertex, you get the y component of that vertex, which is your maximum area already. Okay, it's the same. Okay, yeah, but I like that question because you see how tight or how close are the ideas in quadratic function related. Okay, if you want to get the maximum, you can go through the standard form. On the other hand, for you to get the standard form, you can get the vertex first. In that vertex, you get the y component of that vertex, which is your maximum. So it's kind of going in circle, Thomas. Well, then it means you can go either way, right? Okay, but you can try to do it that standard form, but you will see that when you get the standard form, so that you will get ax equals to negative of x plus minus something, and then plus, you will end up with plus 25, right? But you get the 25 from the vertex. That's also your maximum. No, the standard form y equals to mx plus b, y equals mx plus b, first of all, is not called standard form. Y equals to mx plus b is slope-intercept form. Okay, and that's for line. That's not quadratic for quadratic function. Okay. The standard form of a line looks like ax plus by equals constant. Now that's standard form of a line. Y equals to mx plus b is the slope-intercept form of a line. When it comes to quadratic function, when we have quadratic function, the general form is fx equals to ax squared plus bx plus c. The standard form is fx equals to a times x minus h squared plus k. Okay. Now let me go back. Let me go back. Now we get the x-intercept. Now from there we get the axis of symmetry. Axis of symmetry will be x1 plus x2 over 2. So x equals to 5. So the vertex, that's axis of symmetry. The vertex will be 5 comma something, right? Now then you plug into the function a5 equals to 5 times 10 minus 5. That's 5 times 5, that's 25. So that's the vertex 5 comma 25. So then you can rewrite your area function as negative of x minus 5 squared plus 25. And then from there you read the maximum, right? No need. You can do it, don't get me wrong, you can do it, but it's already right in front of your eyes when you find that 25, right? Okay, you know that vertex will be the maximum value, right? The maximum point. Okay, it happens when x equals to 5 and the area is maximum. The maximum area is 25. Okay, so even before you get the standard form, you already have the maximum. That's what I try to say. Okay, you don't need to go as far as find the vertex, find the standard form. No need. Okay, but that's good though. That's good that you asked that question, such that you realize that you know what, I already have that answer. I just write it in different form. Okay, now suddenly you can connect the idea of the y component of the vertex as the maximum or the minimum value, okay, which also fit into the standard form. Okay, now that's one. Another one, I think, a more interesting question is, I don't remember precisely what the question is, but I think it is like this: find the distance from origin to, let's say x minus y equals to 10. Find the distance from origin to that line. Okay, let me finish this one up and then we take a break. Okay, but so let's say we have this coordinate system and then the line looks like this approximately. Let's say this is the line. This is origin. Now, then when we say the distance from origin to that line must be the closest distance, right? Okay. Now, when I went over this question when I went over the tests with Monday, Wednesday class, I show you the first method. The first method is the following. Okay, this is the first method. Let me do it in red. Okay, the first method, line L is x minus y equals to 10. I will find the line perpendicular to this L. Let me call that L perpendicular, going through 0, 0. Okay, so L perpendicular must be x plus y equals to constant. Oh, how do you get that, Thomas? Remember, perpendicular lines in standard form, you switch the coefficient of, you swap the coefficient of x becomes coefficient of y becomes coefficient of x, and you change one of the sign. Okay, so 1x becomes 1y, negative 1y becomes 1x. Okay, you swap the coefficient and change one of the sign. Now then, because it goes through 0, 0, I plug that in. 0 plus 0 equals to c. So x plus y equals to 0. That's the line, perpendicular line. Now, so next, second step, I will find the intersection of L, line L, and L perpendicular. Now, how do we find that intersection? Well, the intersection, basically, you solve the equation, system of equations of this. Okay, when you solve this, you will get a coordinate, right? You don't just get x equals what, y equals what. No, 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 no. It's more than just that. Okay, you get the x equals what, y equals what, which means you get the coordinate, right? One way to solve this is by addition method. If I add this, I get 2x equals to 5 as 10, so x equals to 5. Therefore, the y also equals to 5. Are you with me? So the intersection is 5, 5. Looking back, the coordinate here is 5, 5. That 5, 5 is the point closest to origin on that line. It's the point on the line that is closest to the origin. Oh, y equals to negative 5, my bad. Yeah, y equals to negative 5, my bad. Thank you. It should be in quadrant 4. Now then, part 3, I find the distance then. What is the distance from 0, 0 to 5, negative 5 is the closest distance. From the line to that point. Okay, 5, negative 5, that's right. So the distance equals to square root of 5 minus 0 squared plus negative 5 minus 0 squared. That is gedebam, 5 radical 2. Okay, now notice that the way I find the distance here, I need to find the closest point first, then measure the distance from origin to the closest point. Okay, now let me offer you a pre-calculus method. Okay, pre-calculus method, we do this. Let P, which is coordinate xy, or be on line L. It means that this x comma y satisfy x minus y equals to 10. X minus y equals to 10. So y equals to x minus 10. Okay, now then, for the distance from origin to P is equal to the square root of x minus 0 squared plus y minus 0 squared. Is it right? The coordinate P is x comma y. The coordinate origin is 0, 0. So this d is x squared plus y squared. Now notice that this distance is now a function of two variable dxy. Now, since we know P has to be on the line, then y equals to x minus 10, then my d becomes square root of x squared plus x minus 10 being squared. Can you follow me? So d is square root of x squared plus x squared minus 20x plus 100. So the distance now is a function of d, a function of x, 2x squared minus 20x plus 100. Now, dx is minimum when 2x squared minus 20x plus 100 is minimum. Agree? The smaller the radicand, then the smaller the distance. Now, so if we can find the minimum value for this, then the square root of that will be the minimum value for d. Okay, now, so going back, so 2x squared minus 20x plus 100, it has the minimum value equals to negative d over 2a. That's quadratic. That's negative b squared minus 4ac over 4a, not 2a, over 4a, which is negative of 400 minus 800 over 8. Gedebam, gedeboom, that's equals to 50. 400 divided by 8 is negative 400. Divided by 8 is negative 50. With another negative, give you positive 50. Okay, now this 50 is the minimum for that guy. So dx has minimum square root of 50, right? Which is 25 times 2, that's 5 radical 2. Done. Oh yeah, I have extra 0. Negative 20 squared, which gives us 400. Okay, basically once we can set up the quadratic function, right, we can get the maximum minimum right away. Okay, now the thing is, once I can get the minimum of the radicand, which is quadratic, once I can get the minimum for the radicand, which is quadratic, then the square root of that minimum will be the minimum for D. Now notice that I find the closest distance, 5 radical 2, without even knowing what coordinate give us the minimum distance. Okay, that's the neatness, the niceness about this method. Okay, now notice that I spent some time on this quadratic function here, not on the theory anymore, but more into the application. How do you use this? Okay, once you can create the quadratic function, bang, you can find the vertex right away. Okay, and you can choose the x. Do you want the x component, or do you want the y component? Okay, now let's take a break. Right now it's 9:23. We come back at 9. Let's call it 25. 9:35. Then we will move to 2.7. Resume recording. Like what I said earlier, that I make mistake in my lesson number 8 recording. When I went over section 2.7 on number 8, I did it incorrectly. In fact, I look at the question, I just saw that I actually wrong. I wrote the question incorrectly. So fx equals to x over x minus 2 gx. Here I use 7 plus x over x plus 4, while it's supposed to be gx equals to 7x over x plus 4. Okay, well, anyway, suppose I use 7 plus x, then this will be the work. Okay, now let me fix that later on. So I will redo this number 8 in my 2.7. But let's start with the theory, okay, which you already have, of course, from my lecture, but let's emphasize it again. This 2.7 consists of 2 parts. The first one, algebra of functions. And the second part is composition of functions. Now, the algebra of function parts. F plus g of x equals to fx plus gx. So the notation f plus g of x, that's not multiplication sign. It's not f plus g times x. No, this notation actually means the following: fx is a function, gx is a function, maybe different function, When you add two functions, you come up with a new function. Oh, your test one only up to 2.6. Test one only up to section 2.6. Okay, so 2.7, what we are doing here, it will be in your test two. Okay, let's come back. Now, the sum of two functions give us a new function. Now, so if the function f, you write f as fx, a function of x, right? G as a function of x, then the sum of these two functions is a new function of x. That's why it's written this way. Okay, the emphasis is that function of x plus another function of x is a new function of x. Okay, that's what it means. Now, then another definition, f minus g of x means fx minus gx. Fg of x means fx times gx. Okay, and finally f over g of x is actually means the quotient of fx divided by gx. Okay, now how about the domain? So let fx and gx be functions with domain A and B respectively. Okay. In other words, domain of F is A, domain of G is B. Okay, now then, what happened to the domain of the algebra of the functions? Domain of F plus G is equal to the domain of F minus G is equals to the domain of the product, which is equal to the intersection of A and B. Okay, so three of these here, when you add, subtract, multiply, they all must have the same domain, and it must be the intersection of those two domains. Okay, now the last one here, the domain of the quotient, is the intersection of A and B, and also all those x where gx, the denominator, is not equals to 0. Basically, you have to eliminate or exclude gx equals 0. Okay, now let me do number 8. For example, first example of the day, number 8 in our textbook. So we have let gx equals to x over x minus 2. That's fx, and gx equals to 7x over x plus 4. Okay, that's the correct functions. Now then, part A, what are the sum, difference, product, quotient? So f plus g of x is, maybe I do it side next step below that, is x over x minus 2 plus 7x over x plus 4. On my book, it's 7x. Yeah, it's not 7 plus x. Supposed to be 7x. So the mistake I make in this video here, actually there are two. I copied the question wrong. It's supposed to be 7x there. And then I suddenly changed this to 4 in my video. Okay, so I make two mistakes in my video. But at least I carry that mistake, the first mistake, correctly. Yeah, okay. That's why I want to go over this question again. There's too many mistakes in that one word. I didn't, I wrote the question incorrectly, but I carried the mistakes correctly, you know, until I make typo with that 7. I wrote that 7 as 4. Okay, now that's why I want to go over this again. Now, and then that's basically the sum of f plus g though. Now, anything else after this is basically combining them, right? Which sometimes you need to do, sometimes you don't need to do, but we are actually done with the sum. Okay, this is x times x plus 4, and this is 7x times x minus 2, right? And then x minus 2, x plus 4 is x squared plus 4x plus 7x squared minus 14x. Combining that, that will be 8x squared minus 10x over x minus 2 x plus 4. Now, to anticipate part B, what is the domain of f plus g? You can see that rational expression here, and you need to avoid the denominator become 0, right? Okay, you need to avoid the denominator to be 0. So it will be all real number except 2 and negative 4. Is it okay? Which, if you look back, that's basically the domain of the fx intersect with the domain of gx. The domain of f is all real numbers, but you kick out 2. The domain of gx is all real number, but you kick out negative 4. Okay, so let's say my ex is 2, let's say my ex-girlfriend is 2, and my wife ex-boyfriend is negative 4, right? Okay, when we get married, then you don't invite my ex-girlfriend and you don't invite her ex-boyfriend. How about that? Just illustration, okay? Just illustration. It could be, life can be nicer than that though. Okay. It's like a two party. If you add two functions, then the people that you don't want to invite must be people, each of them don't want to invite. Okay, now then how about f minus g of x? That is x over x minus 2 minus 7x over x plus 4. Now, when you play this out, you will get something over still x minus 2, x plus 4, right? I think you will get negative 6x squared and then plus 18x. But still, when you look at the domain, it's the same domain, right? The domain is of f minus g is still all real numbers except 2 and negative 4. Okay. Now, part C, the third functions, when you multiply f times g of x, that's x over x minus 2 times 7x over x plus 4. That is 7x squared over x minus 2, x plus 4. Is it right? Then when you look at the domain here, that's the same, all real number except 2 and negative 4. So we have that consistency that the domain of the sum, difference, and product of two functions is the intersection of the domains of the functions that build them. Okay, if I color it, I exclude 2 here, I exclude 4. Now notice that for each the product, sum, or difference, we exclude the same people. Okay, now the thing is what happens if we deal with the quotient. So what is f over g of x? Let's call that part C. That's x over x minus 2, big over 7x over x plus 4. Okay, now then the quotient of two fractions is the product of the reciprocal. To divide by a fraction is to multiply by the reciprocal. Okay, now then we usually cancel the x, right? We usually cancel the x, but you can only cancel that x if x is not 0. You can only cancel that x if x is not 0. Agree? And then you end up with x plus 4 over 7 times x minus 2. Okay, but notice that in your gx, let me see what color I use for gx. The blue. Okay, so in your gx, I cannot plug in negative 4 either. Right? And for my fx, I cannot plug in x equals to 2, which still show up. So the domain of f over g will be all real numbers except those people that you eliminate from f, which is 2, the people that you eliminate from g, which is negative 4, and the people that make the g equals to 0, which is in this case happens to be also 0. Okay, so this 2 is from the one you eliminate in f, negative 4, the one you eliminate in g, and oops, the one that make g equals to 0. Okay, now that's for the sum, difference, product, and quotient of functions. The emphasis will be in the domain talk. When we deal with this, it's more about the domain. Now, the next part is on composition of functions. Part B, composition of functions. Let fx and gx have domains A and B respectively. Then definition, F OG, F compose G, that's how we read that. It's a small open circle, not closed circle. It's not a dot. It's not a dot. If it is a dot, it means multiplication. Okay, not dot, but compose, open circle. It's like the degree notation when we write, let's say 70 degree Fahrenheit, right? Now that is the circle, but instead on the superscript, it's in the middle. Okay, the position is in the middle. So if this is the line here, okay, it's in the middle. Okay, the degree sign has on the top, right? 70 degree Fahrenheit. Okay, but the composition has in the middle. Okay, but not a dot. So when you write your compose notation, don't make it so small such that it looks like a dot. Okay, you may misunderstand it as multiplication. Now, F compose G means F of G of X, which means X be the input of G. The output of that G from X is GX. Then it becomes the input for machine F. Now, this is F of GX, which we call F compose G of X. Okay, now then what happened to the domain? Now the domain of F compose G is equal to the domain of the result, whatever the output, but you need to intersect the domain of G. Okay, now let's see, for example, number 22. Number 22. We have fx equals to square root of x minus 15. Gx is x squared plus 2x. The questions are, part A, find F compose G of X. Now, F compose G of X is F of Gx. Okay, now what is Gx? Gx is x squared plus 2x. Now, F blah is square root of blah minus 15. F blah is square root of blah minus 15. We use x there to represent anything possible. Okay, it can be anything. So if I have F blah right now, and this blah is an ugly guy, right? Okay, if you have F blah, then that will be square root of blah minus 15. Okay. Now, how to find the domain here? So the domain of this F compose G must be the set of all x where x squared plus 2x minus 15 at least 0, right? It's the domain of this, right? The domain of the final answer in which the radicand has to be non-negative. But we also need to take into consideration the domain of G. Now, what is the domain of G? The domain of G is all real numbers, right? The domain of F is at least 15. Are you with me? Okay, now because the domain of G is all real numbers, then we just need to find out what is this. Okay, now we need to solve that though. To find the domain, we need to solve that. So solve x squared plus 2x minus 15 greater equals to 0. But we know that already from test 1, we know that already actually from chapter 1, the end of chapter 1, I believe, where we solve nonlinear inequality. Step 1, critical numbers, long time no see. You have to do it this way. You even need to show me step 1, step 2, step 3, okay? So x equals to -5, x equals to 3. So the sign graph -5 here, 3 here, those are zeros. We have quadratic, so this is negative, this is positive, this is positive. So the solution will be negative infinity up to -5 bracket union 3 to infinity. Okay, so the domain, going back to that domain question, the domain of F compose G is the set of this guy intersect with all real numbers, then it will be just this guy, right? The domain will be just this guy. Now, what happens if what we do is the other way around? How about G compose F of X? That is G of Fx. Now, Fx is square root of x minus 15. Now then G blah is blah squared plus 2 blah. This gives us x minus 15 plus 2 square root of x minus 15. How about the domain? The domain of the resulting functions is the set of all x where x minus 15 should be non-negative, right? And on the top of that, we need to look at the domain of f. We need to look at the domain of f. But the domain of f is still 15 to infinity. So both of them the same, right? So the intersection of the same thing must be just the same. 15 to infinity. Okay. How about number 26? I think. Do I want to do number 26? Let me do this one instead. My own question. My own question. Let me do this one instead. How about when, as simple as I can make it, let fx equals to x squared and gx be square root of x minus 5. Now, take a look on, for example, things that you need to be careful. Okay, it's like f compose g of x. F compose g of x is f of gx. That's f of square root of x minus 5. But that is square root of x minus 5 being squared, right? Which will give us x minus 5. Now, here's the problem. When we answer the question of the domain of that f compose g, you may look at that as, oh, that's a polynomial. So the domain is all real numbers. That's the most common mistake. That's the most common mistake. Why? It is true that the domain of x minus 5 is all real number, but because this is composition of function, you need to be aware that the guy that you can plug in is only the domain of the final result and the domain of G. Okay, but the domain of G is from 5 to infinity. Okay, so it's supposed to be intersection of R and 5 to infinity, which give us 5 to infinity. Are you with me? Now, if you think about it, this actually consists of two machines. Machine G that you go in first, and then you go to machine F. Right? Okay. Now, the output of all of this is x minus 5, which seems to be you can plug in any x. But the thing is, even before you go into machine G, the x that you are allowed to go in only x at this 5. Right? So like, and question like x equals to 0 is not in the domain of G. Right? This will get out. If you don't even put that x equals to 0 into machine G, then you don't expect to put that into the whole machine, the whole composition of these engines. Okay, now let me give you illustration. I don't know if I gave this illustration in my lecture video, but I like this illustration because I visualized this so well. When I saw this myself, I remember composition of function. And it makes me understand the issue of domain a lot more. Okay. I hope you don't mind me recording this. It's personal story though. It's personal story. Okay. When I was in high school, when I was in my, I think that's my 11th grade high school, my mom purchased two machines. The first machine, called that machine 1, is a machine at which if you put in fish, then that machine 1 will separate the meat, the fish meat, the fillet, and of course the bones and the head. Of course, the fish that we put in already cleaned up, okay? They're already cleaned up such that once you put that fish in, then you will get the fillet, you will get the bones, you will get the head. Are you with me? Now then, the meat will be put into machine 2. You put that into machine 2, the output will be meatball. So the combination of these two machines, basically you put in fish here, okay, like tilapia, maybe yellow croakers, okay, and they will do the fillet, and Thomas will be standing here, move the fillet into the second machine, and the output will be just meatballs. Okay. It's how many years ago? This was like 25 years ago. Yeah, this was 25 years ago, even 26 years ago. And the machine runs quite, how to say that, we try not to touch the meat, okay, such that the meatballs, you can say it's like touch free. Yeah, it's touch free, and how to say it, because it was done quite fast, it's really fresh. It's really fresh. Not to say that the fish we get is very fresh, because we live next to a sea. Like it's, how to say that, Indonesia is the largest source of tuna. I hope you know that. Okay, and my hometown is that place, the place in Indonesia. Indonesia is very big though. Indonesia, you can say, is pretty much as big as America, maybe even bigger. And this is Bali here and some small islands. We have some islands here. Okay, now the tuna, if you look at Indonesian map, tuna mostly comes from this area. Okay, above this K letter island, you have Philippines, and then above Philippines you have Japan. Now, so but we have most tuna in this region. We have most tunas actually in this region. The temperature of the sea water is best for tuna to feed. So if you go a bit to the north, you tend to get smaller tuna. Okay. The more mature tunas, the bigger one actually in Indonesian water zone already. Okay, so if you go to, for example, Japanese market and you see the tuna, okay, you most likely you see the tuna from Indonesia. It will say in Indonesia. Okay, now the thing is, like tilapia, yellow croaker, and smaller fish, you can find it here. When I say smaller fish, it's as big as your, let's say your lower hand. If you have this, like it's the size is like this size here, the one here. You know, tuna can be as big as a person, right? Okay, but that kind of fish you can not put into the first machine. It's way too big. So the size of the fish you put into the first machine is basically as big as like maybe as big as 1 liter water bottle. That's approximately the size. Now, when you put in that fish, then the machine will separate the fillet and the bone and the head. Okay, and then Thomas will put that. My mom put that in, so my mom chose the fish right away. Okay, this one is still very fresh. Put it in. Within a couple of seconds, it's already have the fillet, and then I move this fillet into the second machine. Within a couple of seconds, we get the meatballs. Of course, this machine already have the salt, have the ingredient that only my mom knows. But it's so little things such that my mom add more, such that the meatballs here, have a very little extra ingredient, and once the meatball comes out, it has to fall on to ice water. Ice water right away. Okay, now my question to you. What is the domain? What is the domain? The fish, right? That's the domain. Yeah. If you put in fish, then you get fish meatballs. Okay. The way the machine works, actually, it's pretty okay if you actually put in chicken, the drumstick. Right? If you put in drumstick, then you will get the drumstick meat, but the bone will have some meat still stick to it. That's why we don't recommend put in chicken. Okay, now, this is the scary part. I told you earlier that the domain is fish, right? The scary part is what happened if Thomas unintentionally have his hand in here. Right, industrial accident, right? Thomas happened to put his hand here. What do you think the output is? You don't call that fish fillet, you call it Thomas fillet, I guess. And the output will be Thomas meatball. The thing is, it looks like meatball already. You don't realize that it's not edible. Now, you may say, Thomas, you're just so good in making up stories. This is my imagination when I was in high school, when I saw this machine works, right? Okay. My mom said, Thomas, be very careful. That's why my mom didn't want me to operate the first machine. My mom's okay with me to operate the second machine. Okay. Because the second machine has that, like, if it finds bone, it will just stop. It will stop working. Okay. So if my hand happens to get stuck in there, okay, it will stop. It's too hard. The machine 2 will say, it's too hard. I don't want to work on this. Okay, but the first machine will not stop if it finds bone. The first machine will separate the bone from the meat from the bone. Okay, so it seems like my hand is still in the domain of the first machine, but no, you don't want to do that because what? The output still look like meatball later on, but you don't know whose meat is that. Quite scary. Okay, so never let any kid, even almost high school graduate person, to operate the first machine. At first I thought, why my mom's just so strict. So it's just like, if you want me to work, let me work on that one, give me some experience and so forth. But later on I realized it's because out of my mom's love to me. If anybody's hand need to get crushed by the machine, let it be her hands instead of my hand. So it's not because she's being like so restrictive on me. No, it's because she loves me. She doesn't want that happen to me. Okay. Good thing, as when we operate these machines, no accidents ever happen. And my mom's meatballs, actually, we make some very good money from here. Yeah, well, it was produced from my hometown, but we have a chance actually to even send it to other countries. But then we have something else happen, that we have to sell these machines. So from here you see composition of functions, right? Okay, the final output, you should not see what kind of X you can have from the final output only. No, you also need to see from machine 1. Okay, not only the final result. Okay, not only the final result. Okay, I have 5 minutes left. Let me do let me do one more question, but this is my favorite question. You almost likely see this question in my test too. Let me make my own question. For example, let fx equals to x plus 3 over 2x minus 5 and gx be 3x plus maybe 3x minus 4 over 2x minus 1. Let's say we have something like this. And my question is, what is f compose g of x? What is f compose g of x? F of gx. Why I want to ask this? Not only because it is in my test. The reason I ask this a lot in my tests is because it requires your ability to simplify things, to be able to see clearer. What is f compose g of x? That's f of gx. Gx is 3x minus 4 over 2x minus 1. Now the thing is f itself is a rational function. So if you put rational into rational, then you get rational on the top of rational. So this will be, let's see, f blah is blah plus 3 over 2 blah minus 5. This will be blah plus 3 over 2 blah minus 5. This is my blah. Okay, so it will be 3x minus 4 over 2x minus 1 plus 3 over 2 times blah minus 5. What you need to do next is to simplify, multiply the top and the bottom by the LCD. I forgot one. I forgot what one. Let me see. What did I forget?
I think it's right at the bottom where it says 3x minus 4 over 2x minus 1. Shouldn't there be a 3 in front of that? Or no?
3.
Because g of x is 3x. So shouldn't there be a 3 in front of 3x minus 4 over 2x minus 1?
Here?
Yeah.
No, because we are putting this g into f.
Oh, right. Yeah.
Right? Okay.
Yeah.
So if you have f into g, then it will be 3 of something minus 4 over 2 something minus 1.
Yeah. I was looking at the wrong
Okay.
one. Yeah.
That's why I want to clarify this. I mean, it's like playing Legos. It's like playing Lego. Okay, it's just like who goes into where. You see, okay, and that possible confusion is the one that I want to address. Good that you see that common mistake, so that you don't make that mistake in your test. And I want to say that those kind of mistakes are silly mistakes, though. Silly mistakes that everybody knows what to do. Is just like you look at the wrong one. Okay, I say that silly mistake because even smart people make that mistake, including me. Okay, but the thing is, like, once you make that mistake, everything you do after that will be just terribly wrong. So this will be 2 times 3x minus 4 minus 5 times 2x minus 1. Okay, now then from there, let me simplify. I know my time's up, but give me a bit more time. This 3x minus 4 plus 6x minus 3 over 6x minus 8 minus 10x plus 10 plus 5. So putting things together, I get 9x minus 7 over negative 4x minus 3. Now the issue then, what's the domain? The domain of f composed G is all real number except the guy that make this 0. See, right? That's negative 3/4. But don't forget one more thing. You need to avoid things that you don't even plug into G. The domain of G is 1/2. Okay, all real number except 1/2. Right? So you need to exclude that also from the composition of function. So the negative 3/4 is being excluded because that should not be in the domain of the final result. Is it right? Yet you also need to get rid of the 1/2 because it's not even supposed to be going into the first function G. Is it okay? Now, I believe I already gave the suggested homework from this section in my lecture, lesson 8. Please work on that. And also please study from for your test 1 already. Okay, I think we are still a little bit behind schedule. I would like you, you need to watch lesson 9. You need to watch lesson 9. Please watch lesson 9. Okay, but when you watch lesson 9, you will see it will be very beneficial if you can watch, go back to lesson 8. Go back to lesson 8, and at the beginning of that lesson 8, I told you which video I would like you to watch. So in that video, there's another video you need to watch. Basically, I need you to watch, find out how to do syntactic division. And it doesn't have to be my video. So you go to YouTube and type syntactic division. Okay, but syntactic division is so important, so crucial for your chapter 3. If you don't know how to do syntactic division at the beginning of our chapter 3, you will have a very, very big trouble to actually dive into that. Okay, that's for today. See you then on Tuesday.